As we have stressed in several occasions, there is no fully consistent special relativistic theory of gravity. Then, if we want to compare the predictions of GR with those of another theory, the pre-existing theory, that pre-existing theory is the Newtonian theory. And we know that this theory can be recovered from general relativity in the weak field low speed limit. This is the so-called Newtonian limit. Then this suggests that we could write the predictions of general relativity as an expansion or as corrections to the results of the Newtonian theory. These corrections or the expansions should be an expansion in powers of the field and of the speed of whatever system we are studying divided by the speed of light. Okay. This expansion that starts with the Newtonian result is the so-called Post-Newtonian Approximation, and this is what we are going to study first. This will be the first step to study this parameterized Post-Newtonian Approximation or framework. This parameterized Post-Newtonian Approximation or framework is born from the desire to consider the same approximation for other metric theories of gravity. The results should be similar in the sense that you start with the Newtonian result, because all theories which can be consistent, they have to be such that you recover the Newtonian limit, okay? Because we know that Newtonian theory works pretty well in that limit. However, when you study the expansion, you will get different terms or maybe similar terms but with different coefficients. In fact, this framework is such that basically you get the same terms, but you can just adjust the coefficients for a theory, for one theory or another theory. Okay, so you can use those coefficients as parameters, and in a sense you have parameterized a huge family of metric theories of gravity. For each particular value of those parameters you have one theory and one particular post-Newtonian expansion, and you can compare that expansion with the experiments or with the predictions of general relativity. Of course, general relativity is included in this framework for particular values of those parameters. This is why this approach is so good, and this is why we have decided to skip section 2, because in the end we are going to recover this post-Newtonian expansion and many predictions of general relativity from the parameterized post-Newtonian framework. Observe that all the effects in the solar system, since in the solar system is a weak field system where the speeds are small with respect to the speed of light, you could find all the effects that you want in this post-Newtonian approximation. In fact, when we studied the precession of the perihelion of Mercury, we didn't get the exact result, because typically you get very, very complicated expressions which are not so useful if you can get the exact result. But in general, it is also enough to find a good approximation, because again, the speeds are small, the gravitational fields are weak. So in fact, all the classical system tests can be recovered in the post-Newtonian approximation. And if they can be recovered in the post-Newtonian approximation to general relativity, then they can be recovered from this parameterized post-Newtonian framework for the particular values of the parameters that correspond to general relativity. Then, after we construct this framework, we will study all these experiments and all these effects. The deflection of light, the radar echo delay, and also the precession of perihelion or pericenters in a more general case. but in this general framework. Okay, and when you set the values of the parameters corresponding to the parameters or to the values corresponding to general relativity, you will recover what we should have recovered found in section 6.2. Okay, so let us start with the post-Newtonian approximation to general relativity, because this is what will allow us to find generalization. Okay. Now, if you remember lecture 4, you may remember that we recovered the Newtonian theory, or some results of the Newtonian theory, by taking first the weak field limit, and this was still a relativistic theory that we said it was not fully consistent, but it was consistent to a certain level of approximation. And then we took the low speed limit. So these two things constitute the Newtonian limit. Now we want to do this in a much more systematic way. If you look in the book by Eric Poisson and Clifford Will, you will see that this can be done in a very rigorous way. First, this weak field limit, and later the low speed approximation. And but it takes a long time, more than we have in this course. And then I will use what is sometimes called the classical approach. In this classical approach is looks a bit ad hoc, but it gives the same results that you get if you follow this rigorous approach, in which you first take a weak field limit and then this low speed limit. Okay, I recommend you, if you have the time and the interest, to check the book by Poisson and Will. But here I will have to just follow this classical approach because it is shorter. Okay, and it gives the same results. I will point out to the particular points in which there are ambiguities that within this classical approach cannot be solved completely, and that are explained in the when you follow the rigorous approach. In this approximation, one considers the gravitational field produced by a certain matter distribution, which is described by the energy momentum tensor of a perfect fluid. This matter distribution is subject to a slow motion condition. So suppose that this distribution is characterized by some length scale, which is represented by RC. So this is the characteristic size of this matter distribution, and also a time characteristic time scale TC, which is the characteristic time scale in which all the phenomena take place within this matter distribution. This matter distribution can be a galaxy. It can be just two planets. It can be a cloud of whatever. Okay, you can adapt this perfect fluid description to these different situations. So if these are again the typical length scale and the typical time scale, then the typical velocities involved will be given by the quotient. Okay. And this low motion condition that we are going to impose is that this characteristic speed divided by c is much smaller than 1. Okay, this condition is a very extensive condition. So for instance, all the velocities within this matter distribution, including the speed of sound in the body, the velocity of the body, if there is a body or whatever, have to be much smaller than c. On the other hand, if lambda c, okay, which we defined as the speed of light times this characteristic time, this will be the characteristic wavelength of the gravitational radiation produced by this matter distribution, because this is the time scale in which all the motions are produced and so on. Okay, then automatically you find that the characteristic size or the characteristic length scale of this matter distribution is much smaller than this wavelength. So this is one of the conditions, and this is, if you want, a consequence. But okay, this condition can be interpreted as saying that all the matter in this matter distribution is inside what is known as the near zone region, okay, which is the region which is smaller than this characteristic wavelength of the gravitational radiation produced. When you want to study the whole problem, gravitational problem, you have to consider that you cannot just say, for instance, that the planet moves around another around the star, and that's it. In this motion, gravitational radiation is produced, and the complete solution should take care of everything. Okay, this is the complete problem is impossible to solve. So you have to split the problem in pieces and make approximations. For instance, one can study the gravitational field within this near zone region, in which the gravitational radiation can be ignored, for instance. And if your goal is to study the gravitational radiation, then you will have to study a different region, okay, that we are not going to study for the moment. Okay, the first thing that we need now is to estimate to which order on this parameter VC divided by C squared, okay, or another parameter which should be of the same order, because in gravitational systems you just find that typically the kinetic energy and the potential energy are of the same order, so you could use these two parameters to characterize this expansion. Both of them should be much smaller than 1 in the right units. Okay, so if these conditions are satisfied, and we are going to make this expansion in the metric and all the elements that appear in the Einstein equations, okay, we need to estimate how many terms in the expansion in this parameter we need to include. Okay, in order to do this, starting always with the Newtonian limit, okay, in which these speeds are really, really small. Okay, so the first thing that we are going to do is to consider to study the geodesic equation. Okay, and if we are looking at the Newtonian limit and the post-Newtonian limit, then it only makes sense that we look at the spatial components xi, okay, because you are going to recover the Newtonian equations of motion plus corrections, and those equations only involve the spatial components of the spatial coordinates, right? Okay, another problem is that the Newtonian equations appear in terms of the standard velocity, okay, which is the derivative of xi with respect to the coordinate time, and the acceleration, which is the second derivative, also with respect to the coordinate time, and not with respect to the proper time that is what appears here in this equation. Okay, this is the x alpha ds. Okay, so well, if we want to rewrite these derivatives in terms of derivatives, the derivative with respect to s in terms of derivatives with respect to time, we apply as usual the chain rule. It looks like we don't know what else to do, but okay, as you know, this is really useful, so this is what you are going to do. Then the second derivatives, okay, are d square t ds. This is a second derivative with respect to s, so I take the derivative of this with respect to s, x mu dt plus dt ds, and here I apply the chain rule again, so I get another derivative of t with respect to s, or this square. Okay, now I can what I want is this, because this is what appears in the Newton equation, so I write this is equal to x double dot mu minus d squared t ds squared dx mu dt, and all this now comes multiplied, or rather divided, by dt ds squared. Okay, this is in general for the spatial coordinates. Just take the index mu equal to I, no big deal. But we are not interested in t. We want to use instead of t x0, so this would be 1 over c d square x0 with respect to s squared. This is what we have called x double dot 0, and then here dxi dt. Here you have 1 over c dx, so sorry, just x dot and this s square, and dividing. Okay, I have done this because we have the geodesic equations, okay, originally for all the components mu. So they will give us x double dot I and x double dot 0. This is just c squared and divided by x dot 0 squared. Now x double dot I is equal to minus alpha beta I x dot alpha x dot beta minus 1 over c, and x double dot 0 is minus, so minus and minus gives me plus alpha beta 0 x dot alpha x dot beta dxi dt. Okay, now we are going to multiply this term by the x dot alpha x dot beta here and here. Okay, just take into account that I can do it here. F x dot alpha divided by x dot 0. This is dx alpha ds, and this is dx 0 ds, and okay, this is nothing but dx alpha over dx 0, which is 1 over c dx alpha dt. So c squared remains as an overall factor, and we have minus gamma alpha beta I 1 over c dx alpha dt 1 over c dx beta dt, and here I'm going to take this 1 over c with the last term, and again we have dx alpha dt 1 over c and 1 over c dx beta dt, and 1 over c dxi dt. Okay, in order to study the Newtonian limit, we certainly have to split space and time. So I need to expand the sums, the contractions over the indices alpha and beta. Okay, and this is easy. We get gamma 0, 0 I first, and then I have dx 0 over dt, and dx 0 over dt is c, so this cancels these two terms. So the first term is just minus gamma 0, 0 I. Then the next term, which appears twice because of the symmetry, will be of this form. One of the factors of c will be cancelled by the fact that you have dx0 over dt, but the other will not. And in fact, we will have dxj dt and 1 over c. But let me express this directly as vj over c. And the last term will be of the same form. Okay, I don't think I need to explain this much more. It's evidently of this form. Now the second term here, has a common factor vi over c, and here you have gamma 0, 0, 0 plus 2 times gamma 0 j 0 vj over c plus gamma jk 0 vj over c vk over c. This is multiplied by vi over c, and that's it. Okay, and this is really an exact result. We have expressed the Newtonian acceleration. The Newtonian acceleration, just the second derivative of the position with respect to the coordinate time, but using the geodesic equation. So this is an exact result. Okay, now we are going to start taking approximations. So we will assume that vi over c is much smaller than 1, and also that all the fields vary slowly. Okay, so this is part of the slow motion approximation. If matter moves slowly, then gravitational fields will vary slowly. Okay, so we also consider that this basically goes to 0. We take in these conditions the equation that we have just derived. Okay, and okay, this term is too small, this term is even smaller, and all these terms depend in vi divided by c, so the only thing that remains is minus c squared gamma 0, 0 I. Okay, now we expand this term. This is gi0, and here you have only derivatives with 0, so two of them cancel and you only have delta partial 0 g0 0. Okay, 0, and then gij have 2 times 0, 0 j minus partial j 0, 0, but we have assumed that all the derivatives of g mu nu are too small with respect to time. Okay, well, this is not only with respect to time, it's respect to c time, the time, and the only thing that survives is plus, if I have done this correctly, this is plus c squared gij partial j g 0, 0. Now, if gij is approximately, okay, in this Newtonian limit, it is basically minus delta ij, then, okay, all these are approximations. This is minus c squared partial I g00. And remember, well, I have forgotten a factor of 2, that in this limit we said that g00 was 1 plus 2 phi divided by c squared. Okay, and this is minus di phi, where phi is the Newtonian limit in the Newtonian potential in this limit. So this tells us that we recover correctly the Newtonian limit. Now we are interested in the corrections, okay? And this limit is good to this order, to the order gm divided by c squared divided by the characteristic size square, or if this is the same, bc divided by c squared divided by rc. Now we want to improve this approximation, including additional terms, so terms of this order. The terms of this order terms of this order are already included, so we want to go to the next order, and the next order is where you have vc over c to the fourth. So these are terms of basically order 1 over c to the fourth, the ones that we want to include. Okay, if you want to include that, you see that because well, here we haven't got anything, there are no factors of c here. This is because gamma 00I goes like 1 over c squared. So if we want to improve this, we need gamma 00I up to order 1 over c 4. Okay. We also need gamma 00 and gamma 0ij up to order 1 over c cube. Okay. This is, you just examine here how they contribute. For instance, gamma 0ij appears here. It is already multiplied with 1 over c, so you need something to order 1 over c cube. But you cannot have something which is only 1 over c or 1 over c squared, because otherwise you would have obtained already something here at this order. So things start at this order. Now gamma 0I 0 and gamma ijk will be of order 1 over c squared, and finally gamma ij0 will appear at order 1 over c. Okay, what we are doing now, as you see, is to use 1 over c as the expansion parameter. This is another way of looking at the Newtonian limit. It is equivalent. If c is very large, 1 over c is small, so it is a small parameter. But you say, okay, you can say that c is the speed of light. It has a fixed value, so it doesn't make sense to take it going to infinity or anything like that. But it is equivalent, okay, from although it may not look like this, it is equivalent since you always have quotients like this. Okay, you can say that Vc is very small with respect to c, or you can say that c is very large. It is completely equivalent. Okay, and formally you get the same results. Then what you are going to do in order to find this connection at this order is to expand the metric, okay, the components g00, g0i, and gij in powers of 1 over c, where you should, the expansion should start at the Minkowski value, right? So g00 should be 1 plus corrections. Okay, and probably we don't need any more. In order also to get this expansion for the connection, you can see that G0I has to start at order 1 over C cube plus other terms, and Gij will start at minus delta Ij plus times 1 over C squared, and so on. This is the expansion that you expect for the metric. And for the inverse metric, you expect an analogous expansion. Okay, so this will be 1 plus terms of order 1 over C squared, 1 over C4, G0I will be also further, will start at order 1 over C cube, and Gij will start with minus delta Ij plus terms 1 over C squared, and so on. This is what you expect, and then somehow you have to identify or define the coefficients at each order in 1 over C squared. Now, in this conventional or classical approach that we are following, these coefficients, which are functions, and in fact they are called gravitational potentials, are just written, defined in a certain way. Okay, you can take it as a proposal and that as an answer if you want, that we will see whether it works or not. It is guaranteed to work because we know that the result is correct from other places. Okay, but of course a more rigorous approach in which you deduce the form of these coefficients would be much better. Still, this is good enough for us. So because of lack of time, so what we are going to find, okay, and this starts as just a proposal. Okay, we will assume and we will check if this is good enough, that G00 has this form, okay, where U is one of these gravitational potentials. You see that this U is nothing but minus phi. I don't really know why Poisson will take this opposite sign, but okay, phi is the Newtonian potential in the way I have always used it in this course, and these people call it U. Okay, you basically know that there is something like this at this order. Okay, this is what we have found before, but at the next order, the coefficient has this form. Okay, you could have defined some other function, just psi, capital psi, or something else, but this psi minus U squared, this definition, is just like this because, well, you will see that it is useful and simplifies other calculations. So this is why it is defined in this way, and this is good up to order 1 over C6. G0I, as we said, starts at order 1 over C cube, and the coefficient is 4 times Ui, and these are 3 new gravitational potentials. So we have U, we have psi, and we have these 3 Ui's over C cube, and this expansion is good up to this order. And finally, the components, the pure spatial components, are of this form. This is, if you want, a more compact way of writing them. Delta Ij plus 1 over, this is called good to order 1 over C4. Okay, so it starts with minus delta Ij. The next coefficient is proportional to this Newtonian potential. And in fact, you can see that this potential is here if you take the Schwarzschild metric and rewrite it in the coordinates similar to these ones. Okay. So this is what you expect, or our ansatz, or our proposal, as you want to call it. Remember that we have introduced so far these 5 gravitational potentials, and these are functions of time and space that we will have to determine with the Einstein equations, which we will also expand to this order. These are, well, we said that this is the Newtonian potential, that it appears in the Newtonian limit, okay, as phi. We wrote it as phi. But the rest of the terms that appear here are called are post-Newtonian terms. And these terms, let me put them in some other color, are this one, okay, which doesn't appear in the purely Newtonian limit, also this one, and also this one. And just to follow the standard notation, these are the 1pn terms, so this is the first Post-Newtonian approximation. And well, this already tells you that you can continue this approximation and in more terms at higher orders in 1/c. These are the 2pn, 3pn, and so on approximations, but which really lie very completely out of the scope of this course. For us, it is enough to consider these ones. Now, just as we did in the when we studied static spherically symmetric metrics, in principle, remember that we got metrics that depend on 3 independent functions, but we saw that by using our freedom to redefine coordinates, or to perform general coordinate transformations, we could eliminate one of them. Here you can relate these potentials by using a coordinate condition, and the coordinate condition that people use is the harmonic condition. So you say that you use harmonic coordinates. These harmonic coordinates are defined by this equation, where here these x mu's are treated as scalar functions. Okay, so you have 4 scalar functions, each of them is equal to one of the coordinates, and it satisfies this condition. Now, remember that this equation, or the Laplacian, can be written in this way. G mu nu, and for each of these 4 coordinates, since I have used mu and nu here, let me write them alpha, okay? This has to be satisfied like this. This is delta nu alpha, and this means that this condition translates into the condition mu alpha equal to 0. Okay, so this of course is irrelevant. When you work in harmonic coordinates, the metric satisfies this property. And we are going to use harmonic coordinates, so we can impose this condition on the metric, and this condition will relate some of these apparently independent gravitational potentials. In order to find that relation, we need to compute a square root of g and also the inverse metric. This calculation has been carried out in the lecture notes, and there you can see that to this order, to the order that we are considering, the square root of g is given by 1 plus 2u divided by c squared minus 1 over c4 capital psi plus 7u squared plus times of order 1 over c to the 6, although we are only going to need the first 2. Then the inverse metric, the components, are given by 1 plus 2u over c square plus terms of order 1 over c4. So if this is over 2 over c4, psi plus u square plus terms of order 1 over c6. G0I starts also at order 1 over c cube, and it is 4ui divided by c cube plus terms of order 1 over c5, and Gij is minus 1 minus 2u divided by c squared delta ij plus terms of order c1 over c4. Okay, these are the components of the inverse metric that you're also going to need to compute the Christoffel symbols, because we are going to expand the Einstein equations at some point. Okay, so here we are only going to need the zero component of this equation. Okay, and this is basically straightforward. Okay, so just look at this, and you find that this is 4 over c squared, the time derivative of u plus di ui plus terms of order 1 over c4, which are considered, but okay, this is going to be 0 and order by order. Okay, the only condition that we are going to use is this one, and this one. Okay, remember that basically tells us that whenever we find di ui, you can replace it by minus the time derivative of u. This is something that we impose, but which is consistent. It is allowed because you can always make a general coordinate transformation such that this condition is satisfied. Now that we have the expansion of the metric and the inverse metric and also this condition, you can start computing the components of the Christoffel symbols. I am going to compute just a couple of components and then to see how it works, and the rest you can find in the lecture notes. So let me compute first gamma 0, 0, 0. Gamma 0, 0, 0, we needed just to order 1 over c cube. Okay, so anything which is higher than that we can throw away because it will not contribute to the first post-Newtonian correction that we are computing. So we expand the components of the Christoffel symbols. This is G0 first 0. All the components here, the three terms are partial 0, G0, 0. So two of them cancel and you only get one. And then you have G0i, two terms of this form minus a term of this form. Okay, let's look first at this second term. G0i is of order 1 over c cube. Okay, and this is of order 1 over c cube. Delta 0 is order 1 over c. So this is order 1 over c7. This clearly will not contribute. And partial I G0, 0. G0, 0 starts with 1, but there is a derivative. So the 1 is cancelled, and the first term is of order 1 over c squared. So this is order 1 over c cube, and this term will not contribute to this order either. Okay, we are left with this, and we computed one G0, 0 inverse. So it's 1 plus 2u over c squared plus 2 over c4 psi plus u squared. Then partial 0 is 1 over c partial t, and this is 1 minus 2u over c squared, and we can leave the rest outside because we only need the term in 1 over c cube. This term also we didn't need. Okay, this one will cancel with the derivative, and what we get is already of order 1 over c cube. 1 over c squared. So only the multiplication by 1 will contribute to order 1 over c cube, and the next term gives us something of order 1 over c5. We don't need to consider it. Okay, so we have two factors of 2 that cancel, and minus 1 over c cube partial t of u plus terms of order 1 over c5 that we don't need. Okay, and this is the expansion, the first post-Newtonian expansion of gamma 0, 0, 0. Let's also compute gamma 0, 0 I, which I think we only need to order 1 over c fourth. Okay, this one. So we split space and time components. There is 1/2. Okay, and again there are three terms: partial 0, g0, 0 with different signs. Only one of them survives. Partial 0, g0, 0, and then the spatial components. There are two terms of this form minus this term. Okay, and remember that we only need to stay at order 1 over c4. Okay, so now let me look at this term. This is order 1 over c cube. This contains 1 over c. There is a derivative on g0, 0, so this starts at order 1 over c squared. So this is order 1 over 6, and we don't need to consider this term. The other terms will contribute one way or the other, so I keep them. Okay, and I start writing their value. This is minus delta ij, and 1 minus 2 u divided by c squared. Delta ij I already multiplied by delta ij, and so I get 2 divided by c partial t g0 I minus partial I g0, 0. Okay, g0 I is 1 over c4 over c cube, so this is 8 over c4 and ui, and g0, 0 is 1 minus 2u divided by c squared minus 2 divided by c4 psi minus u squared. Okay, with square brackets, and this factor of 1 will not contribute. So this term first, well, the multiplication by this one is of higher order, so we will not take it. It's only the first one, and gives us minus 4 over c4 partial t ui. So we are done with this, and then we have plus. Okay, there are three minus signs here. Okay, because there is I can cancel these ones, and then there is the overall sign. So minus, and the factor of 1/2 also cancels, so it is minus 1 minus 2u divided by c squared, and well, we have 1 over c squared partial I u plus 1 over c4 partial I psi minus u square. Okay, like this. Okay, so now I multiply minus, and this first term just gives us the what you have inside, so this is pretty easy with a minus sign. And now when I multiply the second with a plus sign, I only need to multiply by this one, because the rest is, the next term will be further 1 over c6. So this is minus and minus plus, and 2u, well, 1 over c4 to u partial I u. And now I collect the terms of different orders. The first term is this one, minus 1 over c squared partial I u, and then all the terms with 1 over c4. Well, let me take minus 1 over c4, because I already see that this one is negative. Okay, the one with psi is also negative, so it's plus psi. And then I have minus, I take the derivative, so this is this, and okay, this term contributes in the same way. So gives me 4 plus terms of order 1 over c6, and this is all I need at the 1 p.m. order, first post-Newtonian order. The rest of the terms are computed, as I said in the lecture notes, and they are given by this expression. Now with this result, we can go back to the Newtonian acceleration. Okay, we found an equation for the second derivative of xi with respect to the coordinate time that depended on velocities and also on the components of the connection, and we can substitute these components of the connection there, and ignoring all the terms that are of higher order in velocities and so on. This is straightforward. You just we have obtained only the terms that we needed, okay, and you only need to contract some of them with VIs, VJs, and so on, and just collect the results. Okay, so let me just quote the final result, and this is minus partial I phi. Remember that phi is minus u, plus 1 over c squared eta I, plus terms of order 1 over c4. And this eta I contains the 1 pn corrections and is given by this long expression. So it's 4 times the partial derivative of these potentials ui plus partial I of the potential psi minus 4 times phi partial I phi plus 3 times vi partial t phi plus 3 times vj partial I u j minus partial j u I plus 4 times vi vj partial j phi minus partial I phi v squared, which is vj. Okay, so if you know the values of these post-Newtonian potentials, of the Newtonian potential and of the post-Newtonian potentials, you can compute this eta I, and this eta I contains the deviation from the Newtonian case of the Newton equation, okay, that gives you the acceleration in terms of the force. However, in order to do explicit calculations, we need the explicit form of eta I, which can only be known if we know the explicit forms of these gravitational potentials. The gravitational potentials can be found if we solve the Einstein equations in this post-Newtonian approximation. So the thing that we have to do now is to write the Einstein equations in this approximation, okay, performing the post-Newtonian expansion of the Einstein equations. We are going to compute the Einstein equations in this form. So we have written them in this form, and what we are going to do, okay, this is supposed to be more efficient calculation, but I think you work exactly the same. You take the trace of this equation, and to get g mu nu, the trace of r mu nu, sorry, is r minus a half g mu nu, which is 4 in 4 dimensions. And this gives you 8 pi g over c4, and let's call the trace just t. This is minus r, and then since you find that r is minus 8 pi g divided by c4 t, if you replace this result into the original Einstein equation, you find that r mu nu is equal to, here would be a half of g mu nu, and then r is minus 8 pi g divided by c4 t, and then plus 8 pi g divided by c4 t mu nu. Okay, so here what you get is t mu nu minus a half g mu nu t. Okay, this is the way in which we are going to study the equations or expand them in this post-Newtonian limit. So we are going to find first r mu nu. R mu nu for the connection expanded in this first post-Newtonian approximation, which is given here, is computed in the lecture notes. Let me just compute a couple of components. And okay, I am going to use this expression for r mu nu. R mu nu is equal to 1 over square root of g partial nu square root of g minus a half lambda square root of g mu lambda plus gamma mu alpha beta gamma nu beta alpha. This form is manifestly symmetric in mu and nu because partial derivatives commute. Gamma is symmetric. This is the Levi-Civita connection. And in this term, things are contracted exactly in the way you expect. So it is symmetric in mu and nu also. Okay, this is a bit simpler than computing all the terms that appear in the Riemann-Korotcher tensor and then contract. So it's just a slightly simplified version that speeds up the calculation. Remember that the value of g that appears here, the square root of g, is 1 plus 2u divided by c squared minus 1 over c4 psi plus 7u squared. Okay, plus terms of higher order, I don't bother to write them. And that the inverse, you can easily compute, is just 1 minus 2u divided by c squared plus 1 over c4 psi plus 11 u squared, okay, plus terms of higher order. So let's compute r00. Okay, this is nothing but partial 0 squared, which is 1 over c squared partial t squared of the square root of g minus 1 over the square root of g. then partial lambda square root of g gamma 0 0 lambda, and this gamma 0 0 lambda we can expand, okay, and in time and space components. So there is a term with a 0, okay, and an analogous term with an index I. And then there are all the terms that come from here. This is gamma 0, and this is going to be gamma 0. So first there will be gamma 0 0 and 0 0. So you have this square. Then there is a term in which you have 0i and I0 and 0i. And this term appears twice because then you are going to consider the one which would be 0 0i and 0i0, which is exactly the same. So you get a factor of 2. And then there is a term which is symmetric, which is just this. Okay. Now, if you remember what are the orders of these components of the connection, you see that gamma 0 0 starts at c cube, so r0 0, well, gamma 0 0 0 square will be of order c6, and we can discard it. And the same happens with the term that has gamma 0ij, gamma 0ji. Okay. These two are really of higher order, so these two we just eliminate, and okay, we come here. This already has 1 over c squared, so we're going to introduce the square root of g here, and okay, only the first term will contribute. So you have 2 over c4 d squared t u, and then you have 1 over square root of g, but again in this expansion here only the 1 will contribute, so we are done with that term. Now let's consider this one. Okay, I should write like this, and gamma 0 0 is of order c cube already, so to order c4 the only thing that will contribute is 1 from here and the factor 1 from here. So let me see what it was, gamma 0 0 0, and it is minus 1 over c cube on the partial derivative. So minus and minus is a plus 1 over c4 partial t squared u. So this is another term that of the same form. Okay, now let's go to the next one. So we have 0 0 I, and 0 0 I has two terms, okay, with 1 over c squared and 1 over c4. And so we have to consider, the first one is with 1 over c squared, so only the terms in c squared here and here will make any contributions. Okay, so we have 1 minus 2u over c squared. The contribution of the other term will be of higher order, and here is 1 plus 2u over c squared, and then gamma 0 0 I starts with minus 1 over c squared partial I u minus 1 over c4, okay, and a complicated term that let me call for a moment because I am a bit lazy, just y, okay, then I will rewrite it later. So this is 3 times over c4 partial square with respect to time of u, minus 1 minus 2u divided by c squared partial I, and then we have minus 1 over c squared partial u minus 1 over c4 y, and then minus 2 divided by c4 u partial I u. Okay, these are all the terms now to this order. And then we have, okay, let me collect terms in C4 here. This is 1 plus, okay, and this minus cancels this minus. So first we have 1 over c squared partial I u. I am multiplying this by 1 plus 1 over c4 partial I y plus 2u partial I u, and then I multiply by this second term, and this is minus 2 divided by c4 u partial I u. Okay, again we collect terms of order 1 over c squared. There is only one, this one, and terms of order 1 over c4, and this is 3 partial squared with respect to t plus partial I y plus 2u partial I u minus 2u partial I u. Now you can operate here knowing what y is. Okay, and now this is just a trivial calculation, so I'm not going to do it explicitly. I just quote the result is 1 minus 1 over c4 minus 1 over c4 and partial 2t u plus u partial I u minus partial u I psi. And notice that I have used the harmonic condition, the harmonicity of the coordinates, okay, and I have used that to rewrite this in this form. So this is why there is no 3 here. Okay, this coefficient changes because there are terms of this form in y. Okay, the rest of the terms can be computed in more or less the same way. It's just a question of being patient and not missing factors and signs and so on. So I will just quote the result from the lecture notes. And this is the final result for the Ricci tensor. Now, since we are working with the Einstein equations written in this form, we don't need to take the trace with the inverse metric. These are the Einstein equations that we are using. So we don't need to compute the Einstein tensor taking the trace and so on. On the other hand, we need to compute the trace of the energy momentum tensor and so on. So this is what we are going to do next. The energy momentum tensor, whose post-Newtonian limit we are going to study, is a slightly different version of the energy momentum tensor of a perfect fluid that we studied in lecture 1 and then in lecture 4. Let me write it and then we will see what the difference is. Okay, the one that we consider, okay, restoring the factors of C, which are important if you want to take this Newtonian post-Newtonian limit, is like this. Sorry, there is a minus P g mu nu. Remember that P is isotropic pressure, and sorry, I wrote P. This is rho, and rho would be the energy density. In this case, the energy density is going to be split into rest mass density, which we still call rho, and the proper energy density E. So this is proper energy. density as usual. And this is rest mass density. And since we have one more variable, you need more equations, and the reason for writing this in this form is because we are going to consider that the rest mass is conserved in this system. It satisfies this condition. So rho u mu is equal to 0. And remember that this equation is equivalent to this equation. Okay, it's just a divergence, a covariant divergence, so we can write it in this way, equal to 0, and of course you can ignore this 1 over square root of g. Okay, now the force velocity we are going to write in this form. Okay, we are going to introduce this parameter gamma, which is such that the force velocity takes this form. So you see that gamma is nothing but the component u0 divided by c, essentially by definition. We can find the post-Newtonian expansion of gamma by considering the constraint that tells us that this force velocity satisfies that its modulus, its absolute value, is equal not to 1, okay, because we wrote 1 in units of c equal 1, but now it has to have units of c squared. So taking into account this formula becomes gamma squared. Then the 0 components now are c squared g0 0 plus the 0I components, this that appear twice. There's a factor of c, there is a vi, and then g0I plus the spatial component. So this is vi, vj, gij. Now let me take this factor of c squared out. Okay, so all the velocities appear divided by c. And now we can expand the metric because we know its form, and then we consider the products of this expansion by these velocities divided by c. Then you also have this one divided by c. We are going to stay only to order 1 over c4 inside of these brackets. We know that g0I is of order 1 over c cubed, so this will be of order 1 over c4, so I just don't consider it. gij has the leading term is minus delta ij, and the next term is of order 1 over c squared. So we ignore this second term or the next term, and we keep just the leading order term, which is minus delta ij. And in g00 would be 1 minus 2u divided by c squared. So this is c squared, gamma squared, 1 minus 2u divided by c squared, minus, and delta ij, vi, vj, is v squared divided by c squared. And all these plus terms of order 1 over c squared. Now we are outside of the brackets and we have this c squared here. Okay, from this you find that gamma squared is equal to the inverse of this expression in brackets. Okay, so gamma is just this to the minus 1/2. Let me write it like 2u plus v squared divided by c squared plus terms of higher order, and this will be just 1 plus u divided by c squared plus v squared divided by 2c squared plus terms of order 1 over c4. Okay, and this is the value of gamma, or the expansion of gamma, that we are going to use. Okay, where does gamma appear? Okay, it appears in here, in this conservation law of the rest mass. let me expand this for you. So if we consider partial mu, square root of g rho u mu, which is equal to 0, this is partial 0 square root of g rho u0 plus partial I square root of g rho ui, and then remember that u0 is c times gamma, and the partial 0 is 1 over c partial t, so there is square root of g c gamma and rho, this c is cancelled, plus and partial I square root of g rho gamma vi. Okay, you see that this combination square root of g gamma rho appears many times, and we are going to call this rho star. So rho star is by definition square root of g gamma rho. And what happens with this quantity is that it satisfies this property. Okay, so it is conserved with respect to the coordinate time. Okay, it satisfies this continuity equation, where this is the current of rest mass, and this is the rest mass density. Okay, so this motivates this definition rho star. And now we have also, of course, an expansion for rho star, because we have an expansion for gamma and an expansion for square root of g. So rho star, okay, which is the square root of g gamma rho, is in this component in the end, let me just quote the result because this is very easy to get. It's 1 plus v divided by 2 c squared plus 3 u squared divided by c squared times rho. Okay, plus terms of higher order. Okay, this will be one of the expansions that we will make. And finally, we are going to change the variables from the proper energy density to pi, which is defined as E divided by rho. This is the internal energy of the fluid per unit mass. Now you've seen the definition of pi and the definition of rho star, and also the post-Newtonian expansion of gamma. We can compute the post-Newtonian expansion of the energy momentum tensor that we wrote at the beginning. As usual, you can find the expansion of all the components of that energy momentum tensor performed in detail in the lecture notes. Here I am going to do it just for one component, T00, to illustrate how it works. So the component T00, according to the definition, is just rho plus E divided by c squared plus p divided by c squared, and times u0, so you have u0 squared, minus p times g00. Okay, now we split this first term into rho, which appears as a common factor of 1 plus, here is where pi enters, and then u0 squared, and then p, which is a common factor of u0 squared divided by c squared minus g00. Okay, now remember that u0 was c times gamma, so this appears squared. Okay, so we have rho, we have c squared. We have a factor of gamma and then another factor of gamma that I will use to perform the expansion. Okay, and now I multiply and divide this term by square root of g, because then I find the combination that we defined as rho star. And still I have a factor of gamma here. Then we have p that multiplies gamma squared minus g00. Okay, well, we have rho star, which is a quantity that has a Newtonian meaning, so we just leave it as it is. C squared, then we have 1 plus pi divided by c squared. Then we have 1 over the square root of g, whose expansion is just this. And we don't need higher orders, because remember that the energy momentum tensor is multiplied by 8 pi g divided by c to the fourth, so we don't want to go beyond the first order. And now gamma, whose expansion we computed just a moment ago. So it was 1 plus u divided by c squared plus b squared divided by 2c squared. And the term in which the pressure appears, and we have gamma squared, and this is 1 plus 2u divided by c squared plus v squared divided by 2c squared minus g00 at this order is 1 plus 2u divided by c squared. You see this one cancels, this term also cancels, and actually this term is of higher order. Okay, we want to stay at first order in 1 over c, so this term we just discard it. Okay, this is not equal, but of this order, and then we multiply all these terms. Okay, we only keep terms of order 1 over c squared. You have 1 plus pi divided by c squared, and you have plus u minus 2u, so this is minus u divided by c squared, and then plus v squared divided by 2c squared. These plus terms of order 1 over c squared that we have discarded, and this is the result for t00. It doesn't have, it is really not very mysterious, this calculation for other components of t, so I will just copy the result from the lecture notes. And here it is. Now, since we have written the Einstein equations with lower indices, so r mu nu equal to 8 pi g divided by c4, t mu nu minus a half g mu nu t alpha alpha, the trace. Okay, you want to compute the lower components of the energy momentum tensor. So this is not difficult. Okay, if I want to compute minus t00, I take the alpha beta and I lower the indices as you expect, and you have to be patient because there are lots of terms that appear. Here you get just g00 squared. Then you have a term of this form, but you also have another one which is symmetric to this one, so you get a factor of 2, and then tij gi0 gj0, which is clearly of order 1 over c6 at least, so we will discard this term and also this one. So this is pretty easy to compute, and again in the lecture notes you can find the calculation of all the lower components, and I just quote the result below. Okay, we are not done yet. We need to compute the trace and then the difference. The trace is computed as you expect. Okay, so you would like to compute probably this minus T alpha alpha, and this is a series of terms of the form T00, G00 plus Ti0, Gi0 plus the 0i0i. This gives you a factor of 2 plus Tij, Gij. We'll discard some terms here and like this one, because remember that this goes like 1 over c squared and we are staying at finite order in 1 over c. And okay, if I have the result in the lecture notes, but I just quote it here, is this rho star c squared 1 plus pi divided by c squared minus 3u divided by c squared minus v squared divided by 2c squared minus 3p plus terms of order 1 over c squared. Okay, we're almost there. Now we have to compute these components. Okay, minus a half g mu nu and then t alpha alpha. Again, discarding terms of higher order. Okay, I will just quote the result, which again is can be found in the lecture notes. Okay, and here it is. So we are ready to write the Einstein equations in these variables using this expansion. Again, this is done in the lecture notes for all the components. So let me just do it for one of them, and I will just mention the result for the rest. The 0, 0 is probably the most important one. For R00, we got that it is 1 over c squared partial I u minus 1 over c4 partial t squared of u plus 4 times u partial I u minus partial I psi. Okay, this is the left hand side, and this is equal to minus 8 pi g over c4, because we have been computing everything with this minus sign here, which I can also place in the other side if you want, but you have to be careful. Okay, and so this multiplies 1/2, because already the minus is here, rho star c squared 1 plus pi divided by c squared minus 5 u c squared plus 3v squared divided by 2c squared plus 3 over 2p plus terms of higher order. Okay, and now this is very simple. You just compare order by order terms of the same order in 1 over c squared. Okay, so there is a term, there are no finite order terms. The first term is of order 1 over c squared, and it comes corresponds to this one. So what you get is partial I u equal to 4 pi after you divide by this factor of 1/2, 4 pi g rho star, okay, and with the minus. If I write it in terms of the Newtonian potential that I've been using from the beginning, this is just partial square of phi equal to 4 pi g rho star. This is the Poisson equation for the Newtonian potential, and this is really what you expect. But then there are corrections. Okay, so let's look at the term in 1 over c4. Okay, it comes with a minus, which cancels this minus here, and you have partial square with respect to time of u plus 4u partial I u minus partial I psi, and this is equal to 8 pi g. The factors of c disappear because all terms are of the same order, and then you have rho star pi minus 5u plus 3 over 2 v squared plus 3p, and this is the other equation. Okay, now you can use this equation here. So this plus 4u diu becomes minus 16 pi g u rho star. Okay, and this term can go to the right hand side. Okay, and we are left with this equal to 8 pi g, then rho star pi, and here you have minus 5, and here you have plus 2 in terms of with this factor of 8 pi g. And sorry, I realize now that this should be 4, just because of this factor of 1/2. Okay, so it's 4. This means that this minus 16 is again 4, and minus 5, this gives you minus u. This is 4, sorry, and then plus 3 over 2 b squared plus 3p. And people usually write this in this way, with this divided by rho star. And this is in principle the equation that you have to solve. It is a bit more complicated than a Poisson equation. So people follow this procedure. They define a function f, okay, which is such that df gives you 2u. Again, this number 2 is conventional. Okay, so if you know u, which you do because you can solve this if you have rho star, which is supposed to be a given in your problem, then you know f. And then you can replace here u by df, and this gives you the I of 1/2 of 1/2 of dt squared f minus psi equal to what you have here, 4 pi g rho star pi minus u plus 3 to v squared plus 3p divided by rho star. Okay, by convention, these people that I am following, Poisson and Will, take a minus sign here, so they write this in the opposite order. So they write psi minus 1/2 of partial with respect to time squared of f. Okay, and this combination of capital psi and f is defined as psi, small psi. So in the end, you get another Poisson equation. And here you are everything that you have on the right hand side, rho star pi u, you have computed from the first equation, and velocity and so on. This is supposed to be known. which means that you can just integrate this Poisson equation and find this psi. Okay, we will discuss later how to recover from this psi, capital psi, and so on. For this you need to compute f in more detail. Okay, for the 0i components, this is very simple, and I will just quote the result. You just get this. So again, this is another Poisson equation. And for ij, you don't get anything new. In fact, you get back the same equation that you got first at the 1 over c squared order for the 0, 0 component. And okay, now we have reduced everything to basically 3 Poisson equations. And we need to find just the solution to this f, which is a bit peculiar. Okay, and it is a bit peculiar because all this, when you look at the right-hand side of this equation, the first one, this rho star typically will have a compact support, and this u will be defining the whole space-time as usual. You can have matter in a region of your space-time, and it will produce a gravitational potential, in this case the Newtonian potential, that spreads over the whole space. But this potential will decrease, as we know, like 1 over r, because rho star has compact support. But now that here you have in this equation, instead of something with compact support, okay, as we just discussed, this u, which takes values over the whole space-time. So the solution to the Poisson equation may not converge, and you have to be a lot more careful to find this f. Okay, and only if you find this f, you can find this capital psi, which is the gravitational potential that appears in the metric, and this is in the end what you want to find. Okay, so see, we are reducing the general Einstein equation in this expansion to several equations for the different or independent gravitational potentials, which this is particularly simple because these gravitational potentials appear explicitly in the metric. So if you find them, if you solve these equations, you just go to the metric, plug them in the metric, and you know the metric, at least in this approximation, which is very powerful. If you can go to higher orders, then this is even more powerful and you have a lot more information. Okay, so now we are going to discuss a bit how to solve these equations for u and ui and psi. Okay, so let me remind you that if you have the Poisson equation, then what you do is to find the Green's function, which is a function capital G, not to be mistaken with the Newton constant. I don't think you will make this mistake, that satisfies this equation, that di of G gives you the Dirac delta function in 3 dimensions. And then, as you have studied for sure, because this is a typical example, and in fact we have used this repeatedly, this G, the Green's function, is given by minus 1 over 4 pi and the absolute value of the vector x. So, okay, now that you have G, you know that f of x will be given by the integral in 3 dimensions over, this is some other variable, of g of y minus x, and the source of the Poisson equation gi. Okay. Now, since we know what is the Green's function, you know that this can be written as minus 1 over 4 pi the 3y g y divided by the absolute value of y minus x. Okay, and now we have several Poisson equations. So you know that for phi, okay, remember that this is minus u. This is now the Newton constant, okay, because you have this 4 pi g and here it is cancelled by this. And the integral over y of this density of rest mass divided by the absolute value of y minus x. So you can immediately find this, which coincides with the Newtonian potential. There is no mystery here. If you study Newtonian gravity, you know that the gravitational potential is given by this expression in terms of the mass, which is here identified with the rest mass. Next, the potentials ui are given by a completely analogous formula, okay? And here you have t and y, and the velocities, which are also functions of t and y, divided by y minus x. Okay, and I think there is a minus sign here that probably is not in the lecture notes. There is some minus sign missing somewhere. Okay. And also this potential psi, okay, maybe I should stress that these are functions of t and x. The t is the same t that you get here, okay, and x is this x, and the same for phi. So this is g3y, and then rho star multiplied by pi minus u plus 3 over 2 v squared plus 3p divided by rho star. Okay, all this evaluated at t and y, and everything divided by the absolute value of y minus x. Okay, so now you have these three quantities, and now the question is how do you find capital psi, which requires finding also f. Okay, just from the definition of a small psi, okay, you need to compute clearly f. But the problem is that, okay, as I have mentioned, this Poisson equation, okay, may not have a good solution if you try to solve it in exactly this way, because of the way u behaves. Okay, so the thing is that you could try to find f in the same way, but instead of integrating over the whole space-time, you would introduce a cutoff at some distance in the coordinates. Okay, let me write the formula because probably it's easier to see. So this would be, well, here it is 2 pi because you have this factor of 2. Okay, and you are going to integrate u of t and y. At large distances, this goes like 1 over r, this goes like 1 over r, but we know that this goes like r squared, okay, at large values of r, so this may not converge. So the idea is to introduce this cutoff, so we only integrate for values smaller than this cutoff r, for values of y, which is, if you want the radius, smaller. So we introduce this heaviside theta function, and remember that this function is 1 when the argument is positive, so when y is smaller than r, and 0 when y is equal or larger than r. Okay, so theta becomes negative. So this is a way of introducing this cutoff instead of introducing limits in the integral. This is completely equivalent. Okay, and you know that the solution, okay, here we haven't used it because clearly you don't need that, and the boundary conditions will exclude it. You can add here a solution of the Laplace equation, which is the Poisson equation with 0 in the right hand side. Okay, so F0 satisfies this equation. So this is if you want the complete solution. Okay, now the question is that we know what the u is because we have solved the equation, the Poisson equation that gives it to us. So we just introduce, we plug the solution here, okay, and we just get two integrals. The variable that we use here to integrate I call now z. So we have two integrals in y and z, and here we had rho star t and c. This is divided by z minus y, and then we have also this factor y minus x, and also the theta that introduces the cutoff plus the harmonic function t and x. And now to simplify the notation and study a bit this expression, we introduce a function. Okay, if we write this in this way, okay, star t c and the rest plus the integral in over y, we call k of x and z. It doesn't depend on y because we have integrated over y. And let me write explicitly the expression of this k. So k, x, and z is defined as minus 1 over 2 pi the integral over d3y of theta r minus y divided by z minus y and y minus x. Now we notice that k of x and z will only depend on the difference between x and z because it is clearly invariant under x going to x plus c and z going to z plus c. These two shifts will be compensated by a shift y going to y plus c. Clearly the measure is invariant under this shift, and this is just 1, so it is invariant when y is smaller than r, and 0 anyway for any other value. So if you split this into regions, then in one region this is just not there, it's just a factor of 1, and in the other region the integral is 0. So it is clearly invariant under this. Okay, so given that it is only a function of x minus z, okay, and most likely of this, we are going to compute this kxc first for z equals 0. Okay, and then we will shift c to c minus x. Okay, this is done in full detail in the lecture notes. Okay, it's just not so long calculation, but in which you just re-expressed first 1 over cy minus x as an expansion in the Legendre polynomials in an infinite series. Then these Legendre polynomials are expressed as products of spherical harmonics. You integrate some of them, then the integral is only different from 0 for certain components, only for L equals 0 and M equals 0. So this simplifies a lot the calculation, and in the end you can integrate. Okay, but you have in this expansion, the expansion in Legendre polynomials is different when y is larger than x than when x is larger than y. Okay, so you have to consider these two cases separately, and in the end, okay, this translates into two solutions for k depending on whether the absolute value of x is larger or smaller than this capital R, and the cutoff that we have introduced. Okay, so after you shift again this function z to z minus x, what you find is that k of x and c is equal to this difference, the absolute value of this difference, minus 2r when x is smaller than r, and minus r divided by x minus c when x is larger than r. And what we are going to do is always take r large enough so that this condition is satisfied. So this is the only equation, the form of the solution that we will use. Now you plug the solution back into the equation for f. Okay, and what you get is g, the Newton constant, the integral over c of there is mass density times x minus c, absolute value minus 2r, plus this Laplacian, this harmonic function, sorry. Okay, then you can split the integral, and one of them is just what it is. And the second integral is minus 2 gr, and okay, what you have now is an integral of the rest mass density. So what you get is the total rest mass as a function of time. Okay, so this is total rest mass plus f0 of t and x. Okay, so one possibility, okay, this is you can immediately check that this function is a harmonic function. Just di of this is 0. So you can choose f0 equal to plus 2 dr m of t as a particular case, and in this case there is a cancellation and ftx is given by this. Then you take two time derivatives, and then with this you compute capital psi, and then okay, the conclusion is that you can compute in this way all the gravitational potentials to first order in the Post-Newtonian approximation. We could use automatically, well, immediately this result to compute metrics given certain kinds of forms of matter, but what we are going to do is to wait until we develop the parametrized post-Newtonian approximation. The parametrized post-Newtonian approximation will contain the post-Newtonian approximation to general relativity as a particular case. So instead of doing the same several times, we will just do it once for this parameterized post-Newtonian approximation.